Often, the surrounding world seems ordinary and mundane to its inhabitants. However, just a little closer look reveals that everything is not what it seems. For a long time, we thought that our solar system was just one of many star systems in the Milky Way. It has rocky planets like everywhere else, as well as gas giants. But soon, astronomy made great strides in studying and modeling planetary orbits, and it turned out that our system is extraordinary not because there is Earth, where intelligent beings live, but because of Jupiter. Its orbit deviates too much from circularity. Its elongation, scientifically eccentricity, is 3 times greater than that of Earth. We know that it is very difficult to disrupt the orbit of a celestial body if it has a large mass, and the larger the mass, the more difficult it is. At the dawn of the solar system, when young planets were just forming from the protoplanetary disk, they had flat, circular orbits. To obtain their elongation, there had to be gravitational interaction with some object. Jupiter's mass is 318 times greater than that of Earth and 2.5 times greater than all the other planets in the solar system combined. To pull its orbit so strongly, colossal gravitational interactions are necessary. But with whom? Which planet could be massive enough to influence Jupiter? Uranus and Neptune are also strange. According to calculations, they should have formed in their current positions longer than the protoplanetary disk could have existed. The only reasonable solution to this paradox is to assume that they first formed much closer to the Sun and then migrated further away. But the main mystery in our system is Mars, and rocky planets in general. The farther a planet is from the Sun, the more massive it is. This is because the farther a certain part of the protoplanetary cloud is from the star, the less of its material will be expelled by the radiation and wind of the star. At first glance, this seems to be the case. Mercury is 15 times lighter than Venus, and Venus is 1.18 times lighter than Earth. But Mars? Here the pattern breaks. It is 9 times lighter than our planet. Certainly, some problems can be solved by saying that Jupiter's gravity pulled part of the planetesimals far away from Mars. These are small bodies from which terrestrial planets were formed. However, calculations show that a planet comparable in mass to Earth, or at least half its size, should have formed in Mars' position. And it's not about calculations or theory. Mars lies within the habitable zone of the solar system. If it had an atmosphere comparable to Earth's, it would retain enough warmth for Mars' climate to be similar to a dry and arid one. Mars is located within the habitable zone of the solar system. If it had an atmosphere at least comparable to Earth's, it would retain enough heat to have a climate similar to Earth's arid climate. However, in practice, the atmosphere on Mars is 150 times less dense than ours, and the gravity is too weak to hold a denser shell. This is a fact. Obviously, if Mars were 5 to 9 times more massive than it is now, the 4th planet of our system would be habitable. Observations of other planetary systems show that planets the size of Earth, Venus, Mars, and Mercury are a rarity. Rocky worlds usually have a mass significantly greater than Earth's, so they are called super-Earths. It turns out that all of our terrestrial planets are a kind of anomaly. Astronomers Michael Brown and Konstantin Batygin believe, and most world scientists agree with them, that there is a super-Earth in the solar system. However, it is incredibly far from the Sun, hundreds of times farther from Earth and tens of times farther from Neptune. Naturally, there were no protoplanetary disks of such sizes in our system. In other systems, the migration of planets to and from their star is a common occurrence. A whole class of planets, called hot Jupiters, exists solely due to such migration towards their star. However, there are none of these around our Sun. Gas planets cannot form close to the star, as radiation simply blows the lighter elements into more distant zones. But after formation, a gas giant may lose orbit stability. It can collide with planetesimals that gradually slow its rotation around the star. As the rotation speed decreases, the planet begins to carve rings around its star that gradually shrink. In the process, its gravity ejects objects encountered along the way from the system. As a result, hot Jupiters often leave their star without any terrestrial planets and approach it so closely that they heat up to thousands of degrees. This scenario paints a clear picture. Our own system could have been very different at the beginning. Gas giant planets did not necessarily originate where they are now. Astronomers have built a number of detailed mathematical models of the movement of the bodies in the solar system and have made an unexpected discovery. From the point of view of celestial mechanics, the original region of Jupiter's formation, the one that would be compatible with the elongation A, ND position of its current orbit, is only 3.5 astronomical units away from the Sun, i.e. 3.5 times further than the current distance between Earth and the star. However, Jupiter is currently at an average distance of 5.2 astronomical units from the Sun, which is 250 million kilometers farther away. How did it get there? Computer modeling came in handy here. How did it get there? Here, computer modeling came in handy. Collisions with planetesimals slowed down Jupiter's rotation around the Sun, causing the planet to move slower along its orbit and consequently move closer to the Sun. On its way inward towards the Sun, Jupiter's gravity captured Saturn. Terrestrial planets form more slowly than gas giants and complete their formation after them. Therefore, Earth and Mars were lucky in a way. If they existed at that time, they would have been in danger. Jupiter stopped just 1.5 astronomical units from the Sun, which is slightly closer than Mars. The formed planets would have received too strong a gravitational impulse from Jupiter, and their orbits would have been too unstable. It is highly likely that they would have simply been ejected from the system. Yet Jupiter's migration caused serious problems for the unborn rocky planets. Its gravity did its job. Gas and dust from this part of the protoplanetary disk were literally absorbed by Jupiter, and he had to throw out some of the planetesimals from the system. The region where Mars formed was so depleted of material that it received much less than Earth. But why then did Jupiter not remain 1.5 astronomical units from the Sun and instead turned around and went back? The explanation is only one. Saturn, which was following Jupiter, at a certain stage entered into an orbital resonance with it. This means that the period of 2 revolutions of Saturn around the Sun became equal to 3 rotations of Jupiter, resonance 3:2. The presence of an orbital resonance means that the bodies regularly stand opposite each other. The gravitational interaction between them sharply increases, and their orbits receive serious corrections. The interaction with Saturn pulled Jupiter back just in time. After all, what would have happened if the largest gas giant had not stopped at a distance of 1.5 astronomical units, but had reached 1 unit, that is, the orbit of Earth? Perhaps in this case, there would be no one to ask questions. Earth would have been a small planet like Mars, since Jupiter's walk would not have left it much material for formation. If there was life on it, it is unlikely to be as advanced as it is today. There is an opinion that Jupiter is the protector of Earth today. It protects the planet from asteroid impacts. Well, then Saturn is the savior of Earth. Jupiter's journey could not help but affect Uranus and Neptune. Initially, they were no farther than 17 astronomical units from the Sun. The migration of Jupiter and Saturn eventually threw them onto more distant orbits. They remain there today. Uranus on average is 19 astronomical units from the luminary, and Neptune is 30. But what about super-Earths in the solar system? This is the most massive class of planets, but there is not a single one in our system. They form faster than small bodies of the terrestrial group, so by the beginning of Jupiter's migration, they could have existed in our system. In this case, they would have had an unfortunate fate. They would have been destroyed by falling into the Sun. The remaining material of the protoplanetary disk in the areas where the rocky planets of the solar system exist was too small to form a second generation of super-Earths. All it was enough for was the formation of 4 planets, of which Earth accounts for about half of the mass. But not everything went smoothly. Practically any computer simulation of early migrations in the solar system shows that its current configuration is unlikely. According to the most probable scenario, the planets should be on different orbits, with a slightly different elongation. The problem was pondered over for a long time, until additional planets were introduced into the simulation. It turned out that with 5 giant planets in the early solar system, as opposed to the 4 we have today, the likelihood of forming the system in its current form greatly increases. Almost certainly, there were 5 such planets 4.6 billion years ago, and the 5th was an ice giant like Uranus or Neptune. Furthermore, astronomers Badigian and Brown, who put forward the hypothesis of a 9th planet revolving hundreds of astronomical units from the Sun, note that this is most likely a large object, or one of them, once ejected by Jupiter's great journey there and back. Thus, practically the entire architecture of the solar system is determined by events that occurred before Earth existed. In the place where Mercury, Venus, our planet, and Mars are located now, there could have been a super-Earth, possibly more than one. There were 5 giant planets at that time, not 4. The chaotic migration of Jupiter and Saturn destroyed all ancient super-Earths, throwing them into the Sun, and at the same time, ejected the current 9th planet of the solar system. Jupiter and Saturn themselves moved away from the Sun, and Uranus and Neptune moved even further away. It turns out that the migration of giant planets is a key mechanism that governs the evolution of the planetary system. Those with hot Jupiters may be devoid of Earth-like planets and habitability chances. Their giant planets are so hot because their migration ended close to the star, they didn't have their own Saturn to turn them around. The constant presence of giant planets on close orbits to the star makes the existence of smaller rocky planets in the habitable zone even less likely. But there are systems where there was no migration of giant planets at all. In this case, super-Earths form on orbits close to the star. The most famous such system is TRAPPIST-1, which is 40 light-years away from Earth. It is not yet known how habitable they are, but if they are, there may be more than one habitable planet in such systems, and sometimes even more than 2. Whether this is true or not, we can find out in the next few years, thanks to the James Webb Telescope, which will soon begin operating. Prior to the mass discovery of exoplanets, scientists believed that the solar system was a favorable place for the formation of Earth-like planets and life. But today, knowing about Jupiter's great migration, this hypothesis seems untenable. Earth miraculously avoided destruction and was not thrown away into interstellar space. It seems that the birth of a home for life in our system was extraordinarily difficult, and the number of habitable planets here is noticeably lower than what could be expected in calmer systems.